Good morning, everyone. I'm Shijie Zhang from Huazhong University of Science and Technology. It's my pleasure to present our work, Vassago, a novel blockchain provenance query scheme, which considers the efficiency and authenticity problems in multi-chain scenarios. This is a joint work with Reihan, Jiang Xiaohai, Yisun, Baochun, and Haijing. Here is the outline of my presentation. First, I will introduce the background and motivation of our work. Blockchain has been used in many fields for provenance queries, such as digital finance, medical treatment, and supply chain, since it has many benefits such as transparency, immutability, and traceability. These merits show significant benefits of data provenance towards improved visibility and authenticity, as well as a reduction of administrative costs. For example, in the supply chain for COVID-19 vaccines, suppliers from different countries may need to cooperate to establish a supply chain over a blockchain system. However, due to the lack of scalability of a single blockchain and various regulatory policies from different countries, it is impractical to record the vaccine's transactions from all the relevant suppliers in a single blockchain. Instead, multiple blockchains must be utilized, each of which is deployed in its own country. As a result, cross-chain queries are required to trace the circulation of vaccines across these blockchains. However, compared with single-chain queries, cross-chain queries are presented with two major challenges: lack of guarantees for data authenticity and longer query latencies. Let's consider a multi-chain scenario, which includes blockchain 1, 2, and 3. An item is passed from Alice to Dave. We assume the downstream takes the duty to record the transaction to simplify the transaction operations. To make the cross-chain transfer successful, Eva needs to record the item transfer history in blockchain 3 so that Ford can know the transaction is from blockchain 2 for further tracking. Similarly, Carol needs to record the cross-chain transaction in blockchain 2. In a single chain, it is easy to ensure the consistency of query results, since each party shares the same consensus algorithm. In contrast, there is no such cross-chain consensus covering multiple blockchains. Consequently, results from cross-chain queries may not be authentic, as they may be either inconsistent or incomplete. As shown in this figure, Ford wants to make an exchange with Dave. He wants to make sure the item is indeed from Alice. Therefore, query results from blockchain 2 and blockchain 3 must be consistent, and a complete historical record should be obtained from blockchain 1. The second challenge is the low efficiency. A cross-chain query consists of multiple sub-query tasks on each blockchain, each of which will incur additional query latencies. Theoretically, we can perform queries in multiple blockchains at the same time. However, due to the lack of a trusted dependency for the target in different blockchains, the query is still carried out in the order from the downstream blockchain to the upstream blockchain, which leads to low query efficiency. The main reason for the two challenges is that there is no such cross-chain consensus covering multiple blockchains compared with a single blockchain. Existing query optimizations are oriented to single chain without considering multi-chain interoperations. Existing cross-chain technologies can only support the interaction of two blockchains. However, a cross-chain query usually involves the interactions across more than two blockchains. Our solution uses the name of Vassago, who has the ability to tell the past and future events and locate lost objects. We exploit the relationship among cross-chain transactions and successfully find the cross-chain provenance dependency. This dependency can indicate if a transaction in one chain has a corresponding transaction in the other chains. With this dependency, the consistency and completeness of the query results can be verified, thus guaranteeing the data authenticity of cross-chain queries. Besides, once acquiring the dependency, the sub-query tasks in a cross-chain query can be executed in parallel, thereby accelerating the overall provenance efficiency. Following the above goals, we designed Vassago with two principles. First, to make the cross-chain transactions authentic for the data provenance query, it should be agreed upon by all the cross-chain participators. Therefore, we should use a blockchain named Dependency Blockchain, maintained by cross-chain participators to record the existence of the cross-chain dependency. The second principle is that query results are consistent with what is recorded before. The key to enabling trustworthy dependency is that the cross-chain behavior of each node should be consistent with each other. As a result, we designed the corresponding smart contracts to record the dependency of cross-chain transactions in each transaction blockchain. After that, provenance queries can be performed in each transaction blockchain at the same time. Our key insight is how to define and capture the dependency, by which we can infer the item transfer rules between multiple blockchains. The dependency contains two layers. The first layer describes the cross-chain transaction dependency. It is the smallest unit of cross-chain provenance dependency. A cross-chain transaction dependency contains a group of transactions that happened in different blockchains with implicit dependency. A dependency should contain at least two transactions in different blockchains, because they are divided into two groups called upstream and downstream. The rule is that transactions in the downstream group should happen after those in the upstream. If and only if the number of one of the upstream or the downstream is bigger than 2, the cross-chain transaction is defined as a multi-dependent transaction. Otherwise, it is a single dependent transaction. For example, transaction 4 in blockchain 2 should happen before transaction 3 in blockchain 1. So transaction 4 depends on transaction 3. Similarly, transaction 7 depends on transaction 6. The second layer is the cross-chain provenance dependency. It reveals the relationships between multiple cross-chain transaction dependencies. Similar to the cross-chain transaction dependency, a cross-chain provenance dependency contains a group of cross-chain transaction dependencies. Take acro1 and acro2 as an example. The dependency acro1 between transaction 3 and transaction 4, and the dependency acro2 between transaction 6 and transaction 7 describe the same item's history. Since accrual 2 happens after accrual 1, accrual 2 depends on accrual 1. The provenance dependency can be reused for similar transactions which have the same transaction footprint among multiple blockchains. Therefore, compared with a transaction, a provenance dependency is more static for operation and has fewer states in terms of storage. To guide cross-chain transaction execution and the provenance query, we need to link all the cross-chain provenance dependencies into a dependency graph. It gives cross-chain participators an item's complete dependency view among blockchains. Vassago ensures authenticity by using the cross-chain provenance dependency to guide transaction execution. Carol, a cross-chain participator taking part in the dependency blockchain, as a consensus node to define the dependency. After that, she joins the upstream transaction blockchain and the downstream transaction blockchain related to the dependency. To simplify the transaction execution, we let the downstream receiver to execute the transaction. So Carol takes duty to execute the cross-chain transaction. In other words, she needs to execute transaction 3 in blockchain 1 and transaction 4 in blockchain 2. Let's see how Carol executes transaction 3 and transaction 4 safely. Transaction 3 can be directly executed in blockchain 1 with Bob's consensus because transaction 3 could find its dependent transaction in the same blockchain. Once transaction 4 is proposed in blockchain 2, Vassago first finds its upstream transaction 3 in the same chain. If transaction 3 does not exist, Vassago examines whether the dependency between transaction 4 and transaction 3 exists in DB. If it exists, Vassago finds the dependent blockchain, for example blockchain 1 in this scenario, and validates whether the transaction 3 has been executed in this chain. If so, the newly proposed transaction 4 can be safely executed. In this way, the dependency could be the proof for verifications. Vassago improves efficiency by performing parallel queries on multiple blockchains with the dependency. Let's see how Vassago enables efficient cross-chain provenance queries. Assuming Ford is a cross-chain inquirer, he joins the dependency blockchain and witnesses the dependency. He also joins the related transaction blockchains based on the dependency defined in DB. Finally, he could perform provenance queries in parallel in the related transaction blockchains. Since the cross-chain provenance dependency gives Ford a whole dependency view for parallel queries. For example, Ford knows he could start queries from transaction 3 in blockchain 1 and transaction 6 in blockchain 2 at the same time. The cross-chain data provenance query consists of 5 steps: item trace proposal, dependency query, cross-chain parallel query, result verification, and result return. To be more specific, if Ford wants to make a query among multiple blockchains, he needs to first propose the item trace proposal in transaction blockchain 3. As a response, Vassago queries the DB for the cross-chain provenance dependency related to the target item. Afterwards, Vassago can execute queries on all related transaction blockchains according to the item's cross-chain provenance dependency. Since the item's global dependency among different blockchains has been consented to and recorded by all cross-chain participators. The data provenance query process can be executed in parallel. The query results will be verified to ensure their authenticity. If the results pass the verification, they will be returned to Vault finally. We implement Vassago on top of Hyperledger Fabric, which supports multiple channels for different blockchains. Since our main design relies on the dependency, we implement two prototypes with and without the dependency respectively. We set 8 transaction blockchains for this consensus. Each transaction blockchain contains 4 participators. After that, we use Blockbench to simulate cross-chain transactions. We test the Vassago performance on TPS and query latency in scenarios with and without the dependency. We first compare the query latency of systems with and without the dependency. The experimental result shows that Vassago can reduce the query latency. Without the dependency, the query latency increases as the number of blockchains increases. In contrast, with the dependency, inquirers can perform parallel queries on related blockchains at the same time. So the query latency keeps almost unchanged in Vassago. To sum up, Vassago can significantly improve the efficiency of cross-chain provenance queries. We also compare the throughput between systems with and without the dependency. The experimental result shows that Vassago is scalable. We can find from the figure that, whether the dependency is utilized or not, the system's performance keeps similar. We can conclude that the dependency has negligible impacts on the overall system performance. In conclusion, today's single-chain provenance query can neither support data authenticity of cross-chain transactions across multiple blockchains, nor efficient performance on different underlying blockchains. To that end, we introduced Vassago, which exploits the dependencies of cross-chain transactions to solve those problems in a multi-chain scenario. To our knowledge, Vassago is the first efficient and authenticated cross-chain provenance query mechanism. Our experimental results demonstrate Vassago can reduce the query latency and provide a scalable result. Thanks for listening. If you have more questions, please feel free to contact us.